part 8 of section 4 will be the last part for this section on even and odd functions. You're familiar with the concept of even and odd, hopefully from talking about integers. Not all real numbers can have the even and odd application or even and odd distinction given to it. Only the integers can have even and odd associated with it. So not every function that we encounter is going to be able to have the even and odd label to it. But there are certain functions, and some that we've already seen, that are going to qualify as being even or odd. And the reason why we're discussing it here is because the definition is actually set up very nicely to have a geometric conversation using the transformations that we've just discussed. So let's dive into this definition. Definition 4.6 says let f be a function, okay? Then f is considered to be even if the following condition is satisfied for every x that's in the domain of this function. So let's talk about this condition. First off, f of x. This is going to be some shape. It could be your basic parent function shape. It could be something that I create for you to look at. Some shape. Some function that we're analyzing and wanting to put a label on. F of negative x is going to be that very same shape, but according to that -1 multiplier, we should interpret that as a reflection over the y-axis. And what separates these two statements is the all-important equal to. That means that the shape that you're working with, the shape that you're trying to classify, it should look identical to itself even if it's been reflected over the y-axis. Let me show you an example. It's just a sketch. Squaring function. Y equals x squared. So if I take the squaring function and I reflect it over the y-axis, then the squaring function looks like this. If I had a steadier hand, this would look better, but imagine that everything's lined up perfectly. You can't distinguish between the original shape and the reflected version of that except for the color. Other than that, they look identical. They are equivalent. What that means is that your squaring function is an example of a even function. So this is how we can geometrically check to see if we have an even function. But you may not always have a picture to go off of. So in the next example, we'll talk about an algebraic approach to being able to prove that a function is even, or also if it's odd. And then there's also the possibility that it's neither even nor odd. So the note here even mentions what we're seeing is that even functions are going to exhibit y-axis symmetry, and we can certainly see that here with the drawing. Now let's do the same dissection with the odd function definition. F is said to be odd if this condition is satisfied for every x in the domain. Well, part of this condition we already know, f of negative x. We've got that. But then on the right-hand side of the equal sign, we have negative times f of x. And that tells me reflection over the x-axis. So what this is implying is that a reflection over the x-axis is going to look identical to a reflection over the y-axis. Now it does take a very special type of function in order for these two transformations to actually look identical. For example, the identity function. Just a sketch. Y equals x. And let's say that I wanted to reflect over the y-axis first. If I reflect over the y-axis, my graph will look something like this. Now let's say I take my y equals x, the blue line, and let's say this time I want to reflect it over the x-axis. If I do that, then I'm going to end up with the exact same line that I did when I performed the y-axis reflection. So these two transformations end up being indistinguishable from each other for the identity function. So that means that this is an example of a odd function. Odd function. And it says here that an odd function exhibits what's called origin type symmetry. So origin type symmetry is essentially a 180 degree rotational type symmetry. So if I was to take the origin as my center point, and then I take whatever in the first quadrant here for y equals x, if I take that and rotate it 180 degrees, notice that what I have here in the first quadrant would end up landing right on top of what I have here in the third quadrant. So that's what origin symmetry is to be interpreted as. But we can also see it from the transformation perspective as being these two reflections that are equivalent to each other.